Thanks for staying that late. My name is Daniel Urieli. I'm coming from General Motors at Development Center in Herzliya. And today I'm going to talk about the race for self-driving car, or perhaps more about the challenges presented by self-driving cars. This presentation was jointly prepared with Liat Sles, also working at GM. So the vision of self-driving cars focuses around improved mobility. Mobility is one of the most significant revolutions of modern times, and self-driving cars are going to take mobility to a completely new phase. The promise of self-driving cars includes improved traffic flow, save us the need to find parking spots, autonomous fleets offering us shared rides, flexible shared rides, reduced car accidents, reduced air pollution, and increased productivity by saving gas between 30 minutes to 2 hours every day, depending on how much time you spend in traffic jams, driving in traffic jams. So this slide demonstrates the actual race for self-driving cars. What we see here is just actually a sample of companies working on aspects of self-driving cars today. Different components, starting from computing platforms, sensors, connectivity, mapping, algorithms, security, and complete solutions. And I should mention that this slide is actually 1 or 2 years old, and there are many more players at this point in time.
Anyone not there?
I guess perhaps 1 year ago, someone might not have been, but now everyone is there. So the area of self-driving cars, the main jumpstart was the DARPA Urban Challenge and Grand Challenge. DARPA is the US Defense Research Agency. They offered a competition in 2005 called the DARPA Grand Challenge, which was about autonomous driving in unpaved environments. And this competition was followed by, in 2007, by similar competition of driving autonomously in urban environments. This vehicle is called the Boss, and this is the winner of the 2007 DARPA Urban Challenge. This was a joint collaboration between General Motors and Carnegie Mellon University. And this competition sparked a lot of excitement, both in academia and industry, around self-driving cars. Following this competition, there were a few years of exploration by some companies, and today, as you just have seen, everyone is doing that. There is actually an arms race of who gets there first. Here are some examples. We have the Google self-driving car. We have Uber, General Motors, Baidu, Nutonomy, and there are many others. So next, I'm going to talk a little about what consists of a self-driving car by going over the components based on how information flows in the system. So just a general view, we have a self-driving car that is driven by an AI software agent that serves as the brain of the car. This software runs on some computing platform. You can think of a desktop or a smaller or laptop inside the car. And the main components of this agent are perception, which interprets the world, decision-making, which takes decisions, and action, which decide what to do, and then executing these decisions as actions. So first component is sensors. Autonomous cars have many different types of sensors, and the variety of them are installed on every car. Each sensor has different capabilities, and they have overlapping and complementary capabilities that back each other. So one important sensor is the LiDAR. This is a laser-based sensor that creates 3D point clouds in the surroundings of the car's environment. The LiDAR provides very detailed 3D view of the environment, but has a limited range. Another sensor is the radar. The radar also provides 3D view of the environment, but is much sparser than the LiDAR. On the other hand, it has longer range, so they are complementary in some sense. Another important sensor is the camera, and we can have 1, 2, 4, or even 8 or more cameras on the vehicle. camera, it complements other sensors. It provides dense information. It provides texture, which is necessary for understanding the environment. We also have different, more sensors depending on different setups, like infrared cameras for low light conditions. We have a wheel encoder that tries to estimate the motion of the car based on measuring the wheel rotation. We have GPS and a few other sensors. And these sensors generate huge amounts of data. You can easily make them calculations and easily reach to 1 gigabyte every second generated by all these sensors. And this provides interesting challenges for data mining, machine learning, artificial intelligence communities. I have here a video demonstrating how the output of a LiDAR sensor. I hope everyone can see. I see it, but let's see. Okay, so what we see here is the white dots are the point cloud generated by the LiDAR. We see vehicle driving, and there are vehicles on two sides of the road. The colors, of course, are not given by the LiDAR, but based on a post-processing of this information. Oops. Okay, so some of the challenges in designing sensors include synchronization and calibration. Sensors must be perfectly aligned, so all work on the same coordinate system. They must be time synchronized, so we can use all of them to construct our world view. Different sensors have different ranges, so we need to build a setup that covers the range that is relevant for our task. We need high-resolution sensors. The environment is very rich. There is a lot of information, and we want to get as much as possible of it. We need to design reliable sensors. Some sensors have moving parts, and they wear over time. We need to be able to use these sensors, detect when they have problems, and use the information for robust predictions. Some sensors can get just dirty or humid, and we need to keep operating under all these conditions. We have challenging road conditions, such as weather, different lighting conditions. And finally, main consideration in selecting sensors is the sensor cost. So a single LiDAR until recently costed $70,000. Of course, this is not financially viable for a commercial product. However, prices are going down, and the price is expected to go down to just $500. But still, sensor costs are still an important consideration for selection of sensor suits. Okay, so we have sensors. Next, we need a map. And by map, we see an example of a map. And by a map, I'm talking about a high-definition map, HD map. This is different from the map that we're all familiar with, from Waze or from Google Maps. This is a very accurate map with landmarks, with centimeter accuracy that are used by the vehicle for localization. The vehicle needs to know where it is with centimeters accuracy based on probabilistic state estimation. And these maps are currently necessary for the vehicle. Some challenges in mapping. The main challenges are the cost of map generation. So one approach is just sending dedicated fleets and with high-end dedicated sensors to create these mappings. This approach has problems with scalability, because when the environment changes, we need to send one or more vehicles to update our maps. So alternative solutions talk about crowdsourcing the mapping task. And both approaches are interesting, and they might be complementary. Okay, so we have sensors, we have map. Next, we need to make sense of what the sensor data is showing us. So the vehicle has a perception module which tells the vehicle what it sees. Perception model includes sensor fusion, fusing different types of sensors into a single world view. This is done based on different probabilistic methods. It includes object detection, row detection, and object detection and classification, and row detection, free space detection, object tracking, and free space detection, which is the free space is the drivable area. Here we see an example of the data from different sensors and how we need to make sense of it. We need to find bounding box of objects. We need to distinguish between static and dynamic objects. We need to know their direction they're heading. We need to know the lanes, traffic lights, and many other pieces of information to make good decisions in this complex environment. So some challenges in perception include fusing different types of sensors, combining 2D and 3D sensors. LiDAR is high quality 3D sensor. It needs to be combined with camera that is necessary. It's a 2D sensor. How do we put them on top of each other? And we need to handle occlusions. We need to deal with different visibility conditions. And we want our perception to be robust and redundant. For example, what happens if one sensor fails? We need to keep operating. We want our prediction to be robust. We don't want to make mistakes. And all of that all this perception module need to run on a hardware that can sit in a car, meaning we cannot use a cluster for making inferences and predictions. Okay, so we have sensors, we have maps, we have a perception model, we have a module, and we have a perception module gives us the state of the world. The next step is making decisions. So decision making is about telling the car what to do. There is a whole area of research around sequential decision making in AI. It includes some important subtasks are object behavior prediction. We want to be able to predict what cars, pedestrians, bicyclists around us are doing in the coming seconds to take good decisions. This decision-making module is selecting goals for the car. A goal could be location and speed, desired location and speed within some time from now. And also this optimizing and designing the path and motion planning to reach this goal while avoiding obstacles. An important subtask is negotiation. So when we're in the road, we are in a multi-agent environment. Our actions can affect what other drivers are doing and vice versa. And to take effective decisions, we need to be able to predict the effect of our actions on other drivers' actions. If we don't do that, we might end up with too conservative behaviors. For example, when we're trying to merge into traffic, and all of us know it in Israel, it can be pretty hard if you don't push a little. And this is a type of negotiation. Okay, so challenges in decision-making include driving among human drivers. So it's much easier if all the cars are autonomous. We can design protocols. The cars will obey protocols. All of us know that it's a little harder to make human drivers obey driving protocols. So that the agents need to understand the environment, learn it, and adapt to it. We need to make complex decisions in real time. When we're in a highway, we are in a high speed. We need to decide quickly. In urban environments, we have many participants, lots of uncertainty everywhere, unpredictable behaviors. We need to learn efficiently, guarantee safety, and also do all of that, again, under the computational constraints of vehicle hardware. Finally, we have a path we want to follow, and we need to execute it. And this here comes control theory and the control scientific discipline of control that translates a path into steering, braking, and throttle commands. Okay, so next I'm going to talk about uses of machine learning in self-driving cars. Machine learning has many different uses. We have lots of data, and machine learning is almost everywhere. And whether it's unsupervised learning, supervised learning, reinforcement learning, all of these subfields has use in autonomous driving. And recently, obviously, deep learning is a major building block in each one of these learning paradigms. Here are some examples of how we use machine learning in autonomous driving. Unsupervised learning is used for finding structure in, for example, point clouds. and for unsupervised feature learning. Supervised learning is used in object detection, 2D object recognition, 3D scene understanding and modeling, semantic segmentation, and even end-to-end behavior cloning, meaning to learn how to drive from a demonstrator. Reinforcement learning is used to autonomously learn and optimize sequences of driving actions over some horizon. Here I have another video demonstrating camera-based free space and object detection. I hope everyone can see. So the blue boxes are cars detected by the algorithm using deep learning. And if some of you can see the light blue triangles, these are the detected limit of the free space, meaning the drivable area. Okay, there is also the area of end-to-end learning, and by end-to-end, I mean using machine learning as a single step from raw input to action. So there was a nice paper by NVIDIA in 2016 demonstrating how driving for only 3,000 miles, just using a camera as the main sensor and recording the driver's steering commands, sending it to a deep network, and the vehicle was able to drive in a variety of road conditions and weather conditions. So this is a very nice demonstration. Obviously, it's far from being ready for production. It's not as safe as it should be, but it's a nice capability demonstration. Another success of end-to-end learning is in the domain of Atari. Google DeepMind published a Nature paper about a reinforcement learning agent that is learning from trial and error in any Atari game, or you put it in an Atari game, it starts to try acting in the environment and eventually reaches human level playing, all using deep reinforcement learning. Very simple algorithm, just using deep network. So here are some examples of end-to-end learning, supervised learning. This is what the agent is, or the algorithm, deep network is given. We're giving it raw camera inputs with the steering commands, possibly with the throttle and brake commands. And we learn to generalize to new situations, new images, and how to take actions. And here we have visualization of the most significant neurons. And we see that, interestingly, the network is able to detect features that are relevant for making a decision. For example, it detects a car here, lane marks, a truck. So this is another demonstration of end-to-end learning using deep learning. Okay, the final part of the talk, I want to talk about the challenges for machine learning motivated by autonomous driving from a perhaps more scientific perspective. And for that, I'll start with a brief background on reinforcement learning. So reinforcement learning is a scientific endeavor that is most closely related to natural learning in humans and animals. Reinforcement learning is about learning from interaction to achieve a goal. And reinforcement learning, or RL, has seen some major successes in the recent years. The first big success was a backgammon program that was trained by just playing against itself, no prior knowledge. It played against itself about 1 million games and eventually reached the level of a human champion. Some other impressive successes are in the domains of autonomous helicopter flight, Atari, winning against the world champion in the Go game, a task that was considered at least 10 years away. Robot learning to grasp objects, and smart thermostats learning to save energy, which was a big commercial success in the US. So a comparison between, it may be instructive to compare supervised learning with reinforcement learning according to a few criteria. First one is the horizon. So in supervised learning, we make single decision. We classify, we predict a single label for our input. Whereas in reinforcement learning, we optimize sequences of decisions over some future horizon. In supervised learning, the cost is immediate, and you make a prediction, you either right or wrong, but you know but you immediately know what is your loss. In reinforcement learning, the cost can be delayed. You can think of a chess-playing program that makes a wrong move somewhere in the middle of the game and eventually loses the game. And this program needs to figure out what was the wrong move somewhere in the middle, back in the middle of the game. And this is an instance of a general problem called a credit assignment problem. With respect to feedback, so in supervised learning, you're given the correct answers, or in other words, what to do. You're being told, you're seeing an input-output pairs, you're given the correct output. Whereas in reinforcement learning, the feedback is weaker. It's evaluative feedback, meaning it is some number telling you roughly how good the actions you just took, and you want to optimize it over a long term. In other words, the feedback tells you not what to do, but what is your goal. And potentially, it could be a more robust way to design agents, because you sometimes don't know to teach the agent well what to do, but it's easier to tell it what's the goal and let it figure out by itself. And when the environment changes, the agent can adapt to new environments just by optimizing this goal. Finally, the resulting behavior in supervised learning, we always try to select the best label or action, whereas in reinforcement learning, there is a dilemma between exploration and exploitation. The agent must select suboptimal actions that will give it more information about environment so that it can optimize its reward over the long term. And this is another interesting research problem. So some challenges in applying RL to autonomous driving. The first one is just learn to act in very high dimensional spaces. So I already showed this example earlier. It just demonstrates how much information the agent needs to deal with and eventually take effective actions. Another challenge is sample efficiency. Sample efficiency is central in RL. Data collection in the real world, in robotics, autonomous driving is expensive. We want to learn as quickly as possible. It's not always easy to get huge amounts of data for this purpose. And one might ask, perhaps we can just work in simulation, get lots of data, and then move the results to the real world. Unfortunately, it's not that easy. It's part of the solution, but it doesn't work out of the box, and that's another interesting open challenge. Another property of reinforcement learning is the close coordination of perception and action. So here, perception, which typically uses supervised learning, supports decision later in the pipeline. And these decisions have long-term consequences. So what we have is a perhaps supervised learning algorithm or unsupervised learning algorithm that the goal is not just to achieve good accuracy, but to achieve accuracy that would allow effective decisions later, possibly by an RL algorithm. An interesting property is that the feedback is part of the training loop, in contrast to supervised learning where we train on a training set and then test it on some test set. Here, the feedback is actually part of incorporated into the learning process, and this gives some interesting opportunities. As I mentioned earlier, the feedback is weak, and it's evaluative. No one tells you what the right action to take. So, on one hand, it's easier to collect this feedback. No human is needed for labeling, and it potentially is more robust. However, it's much harder to learn from, so that's another challenge. 1 minute. Okay, I'll go over quickly. There are some more challenges like the need for introspection. We need to know when we don't know something. We need to guarantee safe behaviors. We cannot allow ourselves to crash 1% of the times. And we might need to adapt to different cars and different conditions. Autonomous driving presents challenges for deep learning as well. Again, 99.9 accuracy is not good enough in our case. We have lots of edge cases. We need to provide some uncertainty measure in the predictions if we want to provide reliable behaviors. How to perform deep learning with sparse signals given by radar, LiDAR. The challenge of compression of networks. Again, we need to run on low power real-time platforms. and robustness. There are famous work showing that imperceptible changes can completely change predictions, and again, something we cannot allow in autonomous driving. I'll skip the challenges of end-to-end learning. There is also another related challenge of how to engineer ML systems, machine learning systems. So interesting talk in ICML 2015 talks about how machine learning algorithms on one hand, they're so successful that they're incorporated into commercial systems, and they're actually disrupting traditional software engineering practices since they're very hard to debug, revise incrementally, and verify. And this talk calls for rethinking how we incorporate machine learning systems into commercial products. I'll finish with a fun video demonstrating the application of AI to somewhat unusual parking. And I should stress that this is not how we train our cars, but that's a nice demonstration of AI applied to autonomous driving. So to summarize, self-driving car is the next mobility revolution, and significant improvements in both software and hardware are helping to make this vision a reality. I try to briefly go over the challenges presented by self-driving cars to the AI and machine learning communities in the areas of sensing, mapping, perception, decision-making, and control. So we are excited about self-driving cars at General Motors. We also have a hackathon competition that happens next weekend. The competition focuses on building your own agent. We have about 20 teams, strong teams. We're excited to look towards this competition. The prize is a trip to Las Vegas and participation in CES. That's it. Thanks for your attention, and I'll be happy to take questions.
I think we have time for only one question. Yes.
So the emphasis that you put on reinforcement learning is somewhat surprising. In reinforcement learning, you have to actually do the actions in the world in order to get the feedback. For example, you would have to, crash the car 1 million times in order to learn that crashing the car is not good for you. So this is kind of surprising.
Yeah, that's a great point. So in contrast to simulate an environment where we can crash a car 1 million times, we cannot allow ourselves to do that in the real world. So that's one of the interesting challenges, how you do that. There are some research work on applying reinforcement learning to robotics in the real world, and it's a different paradigm. You need to do it very efficiently. You need to guard the system against crashes or extreme cases. So that's very different than learning in simulation.
Perhaps I will ask one closing question. What happens in countries such as India, where the standard of driving is actually to break all of the rules? What is it that you would like the machine to learn?
So that's another interesting question. So actually we have some of our other presentations include the demonstration of what happened in a junction in India. So we start one step at a time. I think Israel is challenging enough to drive into, and when we are confident here, we might move to India.
Thank you very much. Let's thank the speaker.
Participating in this event, attending in this event. I would like to thank to all the speakers, in particular those that came from abroad. Thank you very much for coming here. I would like to thank Noah for her coordination, which made this event come true. I would like also to thank Eti, Shosh, and Shlomit, and of course our technical team, which include Mendy, Sergey, and Rami. And I also would like to thank you for attending this event and staying so late, and hopefully see you next year. Thank you very much.